And hello to everybody, and thanks also, of course, to Jerry for this opportunity to present some of our work about spectroscopy in this standard range. So let me introduce also myself. So I'm Matjaz Kavcic from Jozef Stefan Institute from Ljubljana, and I will present some of our work. Let's say basically spectroscopy in the tender range. I'll try to combine a bit at the synchrotron and in the lab, as you will see. And I will focus on battery materials, but I will start with more general. So when I have put stuff together, so this is how I have figured it out. So the brief outline is, I'll start with a kind of more general, a little bit of personal view on the standard range itself. I will present briefly the instrumentation that we use for this work, and complete this part with an example of some fundamental atomic study, which is maybe not so close to the community, to this community, but it was in fact how we entered this field, and it's also our original background comes from atomic physics. So I think it might be interesting to show it, and then I will jump to the batteries and stay there till the rest of my talk. So I will start with the synchrotron results and then move on to the lab. So my first slide is, I have used this one. So it's about 10 years ago. I have used this slide at, I think it was a workshop on photoionization and rigs, something like that. And the reason was that I used tender X-rays in the title of my talk. And of course, at that time, this was not really commonly, how I say, established. So what does this actually mean? So I give here like a usual, let's say, usual separation, or how to say, in X-rays, we can usually speak about soft and hard X-rays, and this is commonly known. But you can also get some numbers, of course, where this range one starts, the other one stops, and so on. But already these numbers are, I have put some, but you can find, of course, different. They're kind of arbitrary. So there is a question, whether is this standard X-rays like a tiny gap in between, does it really is just some PR, or if it's really some specific range in any case? So I will start to go with this one. So basically, in my view, or my personal view, is how you distinguish between the two regions. Of course, you need to look at the instrumentation that you use. So when you go to soft X-rays, this is a different community. You use gratings there, and this is not what we are doing. So I'll not speak about that. When it comes to hard X-rays, typically you use crystals to analyze in the monochromator as well as in the spectrometer. And here you can see an example of, let's say, a typical Johann type multiple spherical crystal spectrometer that is nowadays available at different beamlines in different configurations, of course. And this is usually, they call this a hard X-ray instrument. And now the question is, I mean, whether you can use this instrument or such a spectrometer to cover all the range down to the soft X-rays. Or do you need something else according to this classification? And the answer, of course, is yes, you cannot. So for example, I will be speaking about sulfur during my talk. If you want to use sulfur, it turns out that you need a slightly different approach. So therefore, it's justified that we call this like another range, so tender X-ray range. And what is the reason why you cannot use these typical Johann type, very powerful spectrometers? Because it turned out, first of all, that you need to, these Johann spectrometers usually operate relatively narrow angular range because they want to work close to the backscattering angles where the resolution is the best. You don't have these aberrations. And you can always find a good cut, of course, to go higher. But if you want to push it lower, you start to move, you need to somehow, you don't find, I mean, you are limited in the crystal selection simply by the fact, I mean, that the wavelength is increasing, and you are forced to move away for this backscattering angle. And this is now, in this case, this Johann spherical crystal might not be the optimum choice. So you need to consider other geometries, typically cylindrical crystals, and also absorption. Of course, it gets very serious. So ideally, one would need to move the whole spectrometer within within a vacuum chamber. So ideally a windowless, let's say, windowless configuration which can be installed directly to the beamline. So these are these two specifics which makes it a little bit different. And this, therefore, I think it deserves to call this a tender X-range, because you still use a crystal spectrometer, but as you can see, the approach is slightly different. And as an extreme case, I will show you, for example, this paper we have done at the ID26 at the SRF together with Sergei Butorin and Christina, where you can see, in fact, that even to cover, so in this case, okay, Christina has pushed and Sergei the Johann type as much as possible, so they were able to collect the UCL2 edge. But in order to collect both edges, also the L3, we need another instrument, which is slightly different, as you can see, because there we have a full Rix planes. But nevertheless, this is, I think, shows clearly that, in fact, two instruments are needed to cover the full range, and therefore, this is what I will refer tender. So tender means there are no, I would say, strict numbers, but means that you need to work in such a way. So you need to use a spectrometer which fulfills this criteria I have given before. And as we all know, so otherwise, I mean, we are pretty much aware, of course, that despite the fact it's very narrow range, so it's very important. And it covers these elements, which I have pointed out here. So in our case, we were mostly doing this phosphorus, sulfur, chlorine, and sulfur by far was the element we have measured most frequently, and also 4D transition elements. So L edges of these 4D elements are also within this tender range. So we have done some work on molybdenum, ruthenium. So it's also important. And this, of course, like I said, maybe 10 years ago or so, when we entered this field, this was not so, even the word has not been established. And so also the spectrometer was rare. But then, of course, the importance of the region was clearly, I mean, recognized by the community. So, and you can see now that you have several spectrometers coming out at different beamlines. So I have listed a couple of them. And you have seen the very fresh references. So this has been available very recently. And they all of them fulfill this, let's say, the basic criteria. So the first one is they are all use cylindrical analyzers. So first is the von Hamos at the Swiss light source. Then there is at Stanford. So Johansson type single crystal, very similar to what we use. And the final one is the new spectrometer now available at ID26, which is, I would say, the really ultimate tender X-ray spectrometer following the principle of the Johann type. So multiple crystal, very large Solid angle, and everything what goes together. Okay, so at that time I said, I mean, when this was not available, we were using for this range our setup that has been constructed and developed within our lab, and for that purpose of such measurements can be also transported to the synchrotron. And here you can see briefly the main parameters of the setup. So it is like I have already explained before. So we use basically Johansson type Johansson analyzer. So it's cylindrically bent, half a meter Rowland circle radius, and everything is enclosed in a large vacuum chamber. So relatively standard solution. What is a little bit specific is, as I have tried to point out here, is that generally Johansson geometry is, of course, point-to-point focusing, but in our case, we move the sample a bit inside the Rowland circle. And in this case, then the geometry gets dispersive. But the main motivation why we do this is that we had in mind, of course, to measure also emission from, we call this extended source. So not from a point source, but from a larger source. And since, as I said, we are coming from the, let's say, atomic physics, this is our basic background. Our idea was to measure gas phase targets, so to do atomic and molecular studies. And it turned out that of course, this particular arrangement is extremely useful for this purpose. So just, I mean, for the illustration, so this is, for example, the silicon K alpha line. This is the, let's say, the lower part of the range that we can cover with the spectrometer, and the resolution that we get is very decent. Yeah, so this is useful. And this has been measured at home. And when we install the spectrometer at the beamline, this is, for example, an elastic scattering from a gas phase target, I think some chlorine, close to the chlorine KH. And you can see the overall resolution now. So this is now combined, of course, spectrometer and the beamline. It's around half of EV at this energy of the chlorine KH. So this is useful for most of the purpose we have done. And with this setup, of course, we have then at that time, so moved to whenever we were, we wanted to do the experiments in the tender range, we have moved the spectrometer to SRF, to the ID26 beamline to do such work. Here is also a photo of the setup. So this is basically, as you can see, a large chamber with a crystal detector, the stage for alignment. There is another small energy dispersive detector inside, so different things, and there have been some updates during the years also, but the basics is as it is. And from the outside, you see when you come to the beamline, this is how it looks. So basically a relatively large vacuum chamber, because as I said, it's a ½ meter Rowland circle radius, so the distances are significant. And this can be then installed to the beamline. So this, I would say, is one example of a tender X-ray spectrometer. And as you can see, for example, just as an interesting point, this is a photo I have taken, I don't know, 2-3 years ago at the beamline. This is now the new tender spectrometer, and you see still, I mean, the philosophy, I mean, the general principle, of course, is the same. You see the chamber, it's now, of course, with 11 crystals, much more complex mechanics, gets even larger, but it's exactly so following the principle of tender X-ray spectroscopy, so windowless solution, what I have already spoken about. Okay, so now that I have presented briefly, so the range that we are interested in and the instrumentation that we use, so I will just start with so let's say this was our, how to say, starting point, our first experiment we have performed at the SRF within this tender range. And as we are coming, as I said, from, let's say, from atomic physics world, so there was, of course, a very clean and obvious target for us is an argon. So argon has a KH in the tender range. So this was, yeah, very obvious choice for us. And in this study, we have studied multi-electron photoexcitation. So this is, of course, an important topic in atomic physics because it is kind of a direct consequence of correlations between electrons in the atom. And you can see here, I mean, this is a bit condensed, okay, this slide, you can see the absorption spectrum, and you can see another tiny feature there, I mean, above 25 eV above the main edge, you see like another small edge is opening, and this is, of course, multi-electron signal. So this is no structural signal, now we are dealing with atomic target, and it's clearly visible in the absorption spectrum. And it has been extensively studied, of course, in the 90s. A lot of papers you have on different noble gases, on metallic vapors, stuff like this. And one of the problems is that, of course, by the definition, the threshold for multiple excitation will always be above the single one. So this signal is superimposed on the 1s ionization signal, which is, so this continuum is fully open already. So it's kind of difficult to isolate it completely from the single ionization. And now you can see on the left, so an extra value is when you bring in, of course, the spectrometer. So this is now the emission line from the highest occupied state. So it's a K beta line of argon. And you can see in this case a comparison. So when you tune below this double excitation threshold and above, you see a difference. So therefore, you clearly get this double excitation feature, which is now well resolved from the continuum if the resolution is there. And you can, of course, follow it nicely as you tune your beam across this threshold, and then you collect what you could say, of course, a Rix map on doubly excited states, and you get all the details about this multiple photoexcitation, which is kind of nice. I think this example is useful maybe also for the community of people doing analytical work. They do a lot of emission spectroscopy, and maybe you are not aware, as you can see here, that it is not really completely unimportant how you select your excitation energy. As you can see, of course, you need to be aware that, or if you use an X-ray tube, you will always have this kind of contributions. And sometimes, yeah, this should not be overlooked. So it's important to do also fundamental work, or at least to read, yeah, some papers related to that. So basically, I mean, what we have done here, okay, then it was a relatively straightforward and simple experiment, but very informative. So we can get all the information about this 1s3p double excitation. We see, by following the evolution of this line, we see the different mechanisms and so on. So I will not go so much into details here because I want to move on to let's say, more interesting, maybe at least for the community, materials. And it turned out, so also here I will show the next step. So already during our first run at the Synchrotron, we were immediately, of course, also, how to say, directed into the direction of solid materials and sulfur. And this is the, so in the same campaign, we have done also measurements on different mineral standards, and the results of that measurements is this paper, which you can see. So it turns out, of course, that sulfur, or let's say these solid materials, are of course of big interest to the community, and this is this was also one of the first papers we have made, and it is a good one, so still receiving regular attention. I see the citations are coming, and you can see one of the results. So it's this very nice correlation of a very simple energy shift of the K-alpha emission spectrum, and you see, compared to absorption, this correlation can be much, much better, especially within the sulfide series, where you have a direct bonding of sulfur to the metallic cation. And this is, of course, might be very useful or important when you look for the oxidation states, which in many cases turns out that this is what people primarily wanted to do. Okay, so, and based on that, in next experiments, okay, we have many times over and over measured sulfur. So I have selected here 3 examples because I find them maybe a kind of representative, because the first one is on a solid material, so sulfur within a glass material. Second one is a molecular study, so CS2, gas phase target. And the
Matjaz, I wonder if maybe your if either your mouse is not working or your slide is stuck. Can you, were you pointing at the 3 bullet points at the bottom? Oh, now we see it. Okay.
Okay, sorry.
That's okay. No, that's fine. All right, please, yes, go ahead.
I have also lost it before. Sorry for that. So that means, okay, this was just as an illustration that during this experiment. So the third one, okay, is even on a liquid sample. So I think what was sulfuric acid in solution. That means I have lost it again. Okay, it's here. So that means we were many, let's say, many times we have measured the sulfur, and therefore, okay, gathered also significant amount of knowledge, or let's say experience in this energy range. So therefore, it was a kind of let's say the step forward from this. It was a logical step then also for us to move the battery, where we and this, of course, all work we have done and we are doing on the battery samples is in a very nice collaboration with the group for modern battery systems at our National Institute of Chemistry, and they were actually the reason for us to move in that direction, because of course they work on this and other advanced or new generation battery systems. And through our contact with them, we have learned, of course, that an important system, we are not familiar very much before with the batteries, but we have learned, of course, that is also sulfur batteries are very important systems to be studied, and they're pretty, in fact, a lot of knowledge a lot of work is going on in this direction. And here I have put a slide just with some basic data, which I don't even want to go into details. This is not my field, actually, the batteries itself. But what is our contribution that is expected from us here? It's in fact, you see here it's the conversion of sulfur, I mean, the redox reaction going on within a sulfur battery. And what is expected from the spectroscopy is to try to characterize this sulfur conversion. So to provide the spectroscopy, which could characterize the conversion from one to another phase, ideally within a working battery, that means in operando mode. Okay, so this was, of course, we believed that when we have seen that by doing a lot of sulfur, we can certainly contribute to this field. And so, so we tried to enter. And this is, I don't see my mouse again. Okay, here, sorry. So the technique that is used regularly is the X-ray absorption, of course. And if you have maybe already noticed, of course, let's say absorption in the tender range is more, I would say, more commonly available than emission. So there is a lot of work on absorption. And here, I mean, you can see, so there are many references. And typically, this is, I have taken from one reference from our group, from the group from our chemical institute. And this is a typical spectrum, for example, on a lithium sulfur battery, just to give you some idea. So what we have seen this taken at the spectra, and basically the huge signal here is due to electrolyte, which is not in fact electrochemically important, but it's a media to transport the ions. And the most of the conversion is going on here. So this is the sulfur, and then the polysulfides are sulfur being converted to polysulfide. So it's a tiny, tiny stuff. It's kind of a pH here. And so what can we contribute here? Something by bringing in the spectrometer. And of course, people coming from the hard X-ray community, they would immediately say, yes, of course, bring in the spectrometer and do this high energy resolution fluorescence detected XAS, as they saw. So you get sharpening, and this has been done commonly for 3D transition metals. And it's particularly strong for this pre-etch stuff. So it will enhance your, let's say, your visibility in the range, which is the first thing which appears. This is the pre-etch. Okay, so our idea was pretty straightforward. Let's try to do this, bring in the spectrometer, try to do this XAS in the tender range, which is not very common. So, but the first point is whether this will work. I mean, it's not so obvious like in the hard X range, because if you take a look at the numbers, I have again lost my mouse. I don't, sorry. Okay, but this, so the main parameter which you look at is, of course, the core hole broadening. This is what actually limits ultimately your resolution in your absorption spectra. And here you see when it comes to sulfur, it's around half of EV. And if you remember previously when I showed some slides of the spectrometer, this is roughly about the value of the resolution. So it's not straight. Whether we will even gain something, but bringing this is not completely clear. So of course one needs to measure and have a look. And this is, for example, the RIX map on one of the polysulfide standards prepared by our chemistry colleagues. And you can see already, I mean, first of all, because it's a dispersive instrument, we always need, of course, we cannot do line scans across the edge. We need to build a map. You can see already, I mean, that you have this pre-etch, you see here this island perfectly isolated. So, I mean, if I just project this on the, so I do, now you can do a cut, of course, through the plane. And you see, of course, also in this range, you get a significant sharpening effect. So this, at least to me, it was not so obvious before we have tried, because the numbers are good. But as you can see, and I think you see clearly also from the figure, it's not just the absolute number, it's also the shape, of course. It's much more favorable in the Herft XAS, because you see this is instrumental broadening with a Gaussian shape. And this really helps to resolve here. You don't have the Lorentzian tail, but you point out, I mean, you get a very clear resolution in this. So this polysulfide, this typical pH is pronounced much more, I would say, much nicer here. Okay, so then after that, I mean, this work was started. Let's go, let's do it on a battery. But of course, so ultimately, one wants to do it in operando mode, have a battery closed in an in-situ cell, which can take of course, so that it can be inserted in the vacuum atmosphere of our spectrometer. But as you have seen, I mean, we always need to collect these RIX planes, and generally this is a bit time consuming. So one would like to avoid that, because in the battery, it's a delicate process. You don't want to irradiate it too extensively, because you will ruin the electrochemistry. But we decided, okay, instead of a, let's say, horizontal scan, we do a vertical scan that is a simple single emission spectrum. In this case, it's of course not non-resonant, but it is resonant. And we see it, yeah, you see, we decided, of course, we are interested actually in the polysulfide. So we sit on this extractor. And if you record, you see a resonant emission spectra, of course, then this resolution is transferred directly also to the emission. You have a clear separation of the phases which you would like to observe, the transformation one into another. And there you can go, okay, so this is now the real, so operando spectra, so resonant absorption at this pre-etch. And just for, I mean, for curiosity, we have inside also the diode, so we can record also fast absorption. And you can see, I mean, it's not a problem now to follow the polysulfide signal. It's pretty straightforward and very strong, because you can see, of course, you excite resonantly, you really enhance the sensitivity for the polysulfide product, for the polysulfides. So even, yeah, if I will find my pointer, okay, in the middle one, you see, for example, this is, okay, the initial state, and then right from the start, you don't see anything in the absorption, you have clearly already a signal here, and when you develop here a tiny shoulder, it's already dominating here. And the electrolyte, which is kind of a background in absorption, it's here is suppressed drastically, so it goes out, it's not important for you. So this turns out to be, of course, very useful for, especially for the polysulfides, and we have, then you can follow this during the cycle. I mean, you have, of course, you will face a problem with the in-situ cell and stuff like that, but the spectroscopy itself works very nicely, and we have done this rather, I mean, straightforward. And later on, of course, we have, so this study which I have shown was on a, that's a kind of a first time we have chosen the lithium S, so the standard system. It was not about to learn so much about the material itself, but mainly to establish somehow the methodology. And this turns out to work nicely. So we move on, and then this is the next system we have studied. If I really have problem with this, difficult really for me. It was the magnesium sulfur battery. So you can see here, basically, I mean, of course, from the point of view of material, this was new, this was very interesting, but the methodology was exactly the same. So we used the same approach, and it was possible to identify that basically the mechanistic, the mechanism is basically exactly the same as from the lithium sulfur. So this was so this kind of spectroscopy turned out to be very useful. You can see even was selected as a highlight at the SRF, I don't know, a couple of years ago. So that means we were happy, and by this we have somehow, I believe I used to say, we have somehow added the tender emission or resonant emission or RIX, if you want, to the, let's say, portfolio of these techniques that are used in battery research. Okay, so this is the last slide about the synchrotron work.
Why don't we pause for a moment for questions then?
No problem.
Okay.
Here or?
Right here, yeah. This, or do you have one more slide on synchrotron?
No, I will continue. This one is still on synchrotron, but we can pause.
I'm sorry.
I continue with this one, and then we pause. Okay, I agree. Thanks. So this is the last one, and I want to show it because it will connect somehow later on the emission work in the lab. So this one was done on standards. So from the left, the picture is taken from this paper from the Prendergast group from Berkeley. This is a pure theoretical work. So they calculate, this is a calculation of KH absorption spectra of sulfur these polysulfides within the electrolyte. And you can see the results of this calculation, and they show that, of course, this pre-etch is in fact the signal from the terminal sulfur atoms within the polysulfide chain, and these are from the internal ones. And then they predict that the intensity of these two can be used to select also, let's say, the chain length or something. So to identify not only the polysulfides, but also which of the polysulfide are being tested. This is something which battery people would like very much, but it's very difficult. And we have done, of course, also the measurements. So this is collaborative work with the people from CEA, from Grenoble. They have provided this polysulfide standards in solution now, so the closest approximation to the real stuff. And you can see, of course, that you have now a nice systematics of this peak. So, and then we can easily, doing something like that, we can quantify this ratio and compare it to the theoretical prediction, and we confirm the theory nicely. And then we get just, you can see, so when you go to the shorter polysulfides, we get some deviations. And this is explained by the, of course, it's not a problem of the theory or of experiment, it's a problem of the sample. So it's basically impossible to somehow synthesize these short chain polysulfides in the lab. And so this is well expected. It's can be explained due to these disproportionation reactions and then the change of the solubility as you go. So you get some precipitation. And this is a kind of also nice result. And I will come to that later. You will see, I will try to remind you when we come to the lab work. So I will pause here. Okay, Jerry, and then we move to the lab.
Very good. All right. People should keep putting their questions into the chat. So to begin, Konstantin, you had a question?
Yeah, thank you. Yeah, first I want to ask instrumental questions. Mm-hmm. Then at the end, I think more general discussion about double excitation. But this instrumental, in the Johansson spectrometer, in this square-shaped, mm-hmm. The detector was position sensitive, I guess.
Yes.
You always use it in dispersive mode, or you also compared it with scanning spectra.
No, we always move the sample inside, so there is always a dispersive mode of operation. That means we always use a CCD camera as a position sensitive detector. And we of course, we can change a bit, I mean, the position of the sample, but we have never worked point-to-point focusing.
But are you free to choose among point-to-point? Are you free to choose among point-to-point?
No, we cannot move because it's a big chamber, so there are fixed entrance ports, and you can change a bit, yeah, the position relative to the focal point of the circle, but you cannot exchange from one to another.
Because the doubt is, of course, that in energy dispersive, not all energies are reflected with same weight. Yeah, so there is some instrumental function which is unknown, or you have to guess it. So then, yeah, compare against a scanning spectrum would be, of course, more direct. So you didn't do it?
No, but I mean, generally when we measure, so typically we don't move. I mean, usually, I mean, for example, we stay at one fixed position, and across the, let's say, across the length of the detector, these variations are not really substantial. And when you move from one angle to another angle, then of course, then there are bigger. But usually we don't do such measurements. So to compare, really, I mean, to, let's say, to intensity of the lines, which are, let's say, at very much different angles. But usually in our case, we sit in one, so we don't move along. We don't move a lot. And then it's these variations across the detectors are very, very small. I mean, so we don't even consider that usually.
Okay, thank you.
All right, Yang Ha, you have a question?
Yeah, so based on my understanding, you kind of use two ways to quantify the number of different species of sulfurs. One is based on the XAS, and the other is based on fitting the XES. And can you comment on the difference of the two techniques, like which one has like higher resolution or lower error bars?
Yeah, I would say, I mean, in fact, in all on these experiments I have shown, we always collect also absorption. It's relatively straightforward. So we install also just a diode. These are concentrated sample, of course. So we put a diode inside and we record both. And I would say when it comes to, I mean, to quantify each separate, let's say, phases, there is not a, it's difficult to say. I would say it's comparable. So even it's more complicated with the rigs because you have certain weights, I mean, because of course you excite resonantly. So there is not a direct relation between the intensity of your signal and the concentrations. So in this case, I would say even absorption is more straightforward. But when you are interested in, for example, just in polysulfides, then it's much, I would say, much more effective to use the rigs. It's very fast, it's very sensitive. And so we have done with the people from CIA, for example, observed some effect of the particle size. And you really, it's immediately you switch on, you change the potential, you see the formation of the polysulfides immediately. And if you have a good normalization, which is not so difficult, I would say for the polysulfide itself, this is favorable for sure.
Thank you. This is very
if
helpful.
I have answered, yeah, sorry.
Really interesting. I have a question. Your resonant XES data that showed the very sharp features for the lithium sulfide and had the small bump for, I think it was the electrolyte. Could you go back to that slide?
Of course. This one, yeah.
Yeah. So it took me a minute or two to understand, and I just wanted to point, I thought it was really fascinating. So it's not the case here that the electrolyte peak has shifted down 5 volts, right? It's that it's only resonant Raman scattering you're seeing there. Am I correct?
Of course, this is the,
Yeah.
I mean, it has shifted, but this is not non-resonant emission. So therefore, this is a RIX, yeah, resonant scattering.
Yeah, it's resonant Raman. You've got the cutoff because of energy conservation, because of the shift of the edge. Am I right that if, oh, sorry, go ahead.
No. The shift will be exactly the same as in absorption. So if you tune here, I mean, the shift, as you can see, within the absorption, you will get the same shift in the emission. So
right, but opposite.
Opposite direction, of course. The one which is here, the first one will appear at highest energy in RIC. So it's just somehow mirrored around.
Yes. It's due to energy conservation. My question was, if you do this non-resonantly, am I right that the electrolyte then gives a background that's at least as big as what you're looking for?
Yeah, it will be overwhelmed by the electrolyte. So
that's what I thought. It's just a great use of resonant XES here to completely cut off what would have been a very large background. I like that very much.
This is the electrolyte, and you see it's negligible. You don't even take care about that. And here, of course, when you do absorption, it's the majority of your signal, and it's not what you are looking for, of course. Yeah. Very good. I think this is very useful. Yeah.
Okay, you should continue with your talk. Thank you.
Thank you. So with this, I will finish with the synchrotron stuff, which is very nice, of course, and I like, and I will show, this is okay. I will move to the lab. So, and usually this is the photo of our lab. Usually when we say laboratory emission, for example, everybody, of course, thinks about the spectrometer and the X-ray tube. So in our case, as you can see, this is not really the case. So we have a slightly larger laboratory. We have 2 megavolt electrostatic accelerator, tandem one, so to produce ion beams, and these are used for different techniques, so which are not so relevant now for this discussion here. But of course, you see in this at the back, there is our chamber, so installed at the -30 beamline. So that means we can also provide MEV protons, typically we use on our specimen. And then, of course, this is an effective way of inner shell ionization, and you will get X-ray emission. So non-resonant, of course, because these are charged particles. And then if you put in the spectrometer, you can do what you say X-ray emission. So, and this is just for the comparison. So you can see, I mean, this is zinc sulfide. The red one is the non-resonant emission recorded with the same instrument at the SRF, and the black one is at home. So basically, with using emission in the lab, you can record quality spectra, of course, at home. And we do this, of course, regularly. So you cannot, I mean, always go to synchrotron. And this is, we feel, of course, that this is important. So therefore, I mean, we have systematically started to study, of course, the emission, what it can actually bring us, what are, let's say, strong points, maybe weaknesses, and so on. And this is, so this has been done extensively in the PhD work of Marko Petric, who is was a PhD student at that time, now is a postdoc in our group. And within his thesis, we have done really a systematic study, especially we're interested in this phosphorus, sulfur, chlorine. So done a lot of measurements, different compounds, different oxidation states, geometries, everything. So, and Marko has done extensive calculations, DFT calculations, to explain this valence to core spectra. We have established these very nice linear relations of the shifts for all three, let's say, elements. So a lot of work has been done, and it became pretty clear, of course, that emission is very useful. So it can provide a lot of information. So this was a kind of a first step, let's say. We have started with the standards, and with this we have somehow established, let's say, the tool or the approach that is required. And of course, it's not, we have later on even, of course, used this, I mean, to do some real analytical work. For example, this is an example of some biological tissue. It's a mushroom. So it was a project to determine the amount of this inorganic and organic compound within the mushroom tissue. This is, I don't know, concentration a few thousand of ppms of sulfur in this mushroom. And as you can see, so the organic is taken, I think, from the ground, the 6+, and then it's metabolically, I mean, or just the opposite, inorganic, so sulfate from the ground, and then it's metabolically reduced into 2-. And this ratio is important for the biologists. So it was pretty straightforward for us to do that. So you don't need to go to synchrotron. That means this was like the first step, but of course this is a relatively easy, because you are lucky you have a big change of oxidation state, and this is the favorable case, of course, even though sometimes it's good, of course, to dealing with such case because it's not so difficult. But our aim, and this is just an example, that means, okay, we have also bridged this first level, so we are also able to analyze this, let's say, relatively simple cases. But our goal was already when we started this, and we were at that time we were already doing work on batteries, so we were curious about the sulfur. And this is, of course, much more complicated case, because as you can see in the top right corner, of course, this conversion now, it's, of course, the change of oxidation state or the electronic structure is relatively tiny, and it goes gradually. So from one phase to another through this polysulfide. So we should not expect something spectacular, some big changes. And it's a question whether we can measure this. So these are, for example, the two standards which represent both, I mean, initial and final state, and you never get 100% conversion. So this would be an ideal case, which you will never achieve. But okay, we have asked our chemistry colleagues, they have prepared standards, and so at least the closest approximation to this polysulfide. And when you measure this, you see it's very nicely, I mean, even within this tiny, we know about this linear relation, pretty linear, this good correlation among the broad energy span over different oxidation states. But now we are speaking about within a very tiny interval. And you can see that you get a very nice correlation, even though the shifts, of course, are very small. You can see there, you are speaking about, I don't know, 100 millieV. So it's difficult to measure this. You need to have a good precision reproducibility, but it's there. We have done this many times over and over, and it is really systematic. So this is, of course, looks reasonable. I mean, you can measure this, of course. And then you go the next step, you take the standards and you go to valence to core, which should be more, let's say, more indicative, because, okay, here, I mean, the sensitivity should be higher. Of course, you come directly from the valence state. And this is the evolution of the spectra. So you can see this sensitivity, I mean, by eye. But now we were here thinking how to proceed. So, and then finally we have decided, let's go with a simple empirical approach. So I plotted here this quantity, which has been again somehow borrowed from the people doing, let's say, 3D transition metals emission. So they used to determine the spin state. So this is very simple. So it's an area difference relative to the reference spectrum, which is in our case this pure sulfur, which is the initial state of the battery. So just take the difference of the normalized spectra, of course. And you can see here you again get a very nice correlation with the average charge of the sulfur, which means basically that with the emission you can follow this. There should be, it should be, I mean, possible, and so therefore, okay, we move on. And we have, so the next step usually it's to go so-called, we call this Xc2 emission. So that means that you take the cathode, so the chemistry colleagues have run in parallel several batteries which are stopped at the different points along the cycle, and then they of course disassemble it and they make a sample, I mean, in a form that in a pellet, so they put the cathode out and they put it in a pouch cell so that you can put it in the spectrometer. And we have, and this mimics well, of course, the dynamics in the battery. And you can see here we have measured both series alpha and beta series, and we can really see nicely the reduction of sulfur through the cycle. Just the last point is surprisingly a bit lower, but this has been also explained like this is not a problem of the measurement, but it's expected as a so-called shuttle phenomena. So you lose some of the active material through the process in the battery, and you see you can even somehow verify the amount of the sulfur that has been converted. It doesn't go all the way to 2, of course. So this looks reasonable, and they are consistent. This is also important. So both series. So that means, of course, that alpha and beta both can be useful, even though alpha one could be skeptical, but they show quite okay. So this is the results you can see in this paper with more details. It just came out. And of course, so the next logical step from here would be, of course, operando. And there is also an example of operando, in fact, in the paper, but I have not put it here because it's not so representative, but it shows a proof of principle. We see, of course, the reduction there, but it's difficult because it turns out that MEV protons are not really ideal. They are high energy particles. And in this case, of course, an X-ray tube would be much better. So the problem is, of course, to measure a static sample is not a problem, but when you hit the battery, you start to modify the electrolyte, and the electrochemistry is gone. So we have tried several things, and it's not easy, but it can be done as it's. So for more details, you should check the paper. Okay. So this was, in fact, I would say, promising results. We were happy with that. Of course, maybe to a good listener, like for example, maybe Jerry was mentioning before the electrolyte, this I have, okay, I have not, I mean, here it is important, of course, our chemistry colleagues have prepared a battery which has electrolyte which is free from sulfate. And this is necessary because otherwise you will have, your signal will be overwhelmed with a sulfate signal, and we have not even tried that. But they are very skillful, so they have different electrolytes, and I mean, to be honest, this needs to be mentioned. So for this particular type of battery, this is sulfur-free, the electrolyte. That means we don't, because electrolyte goes everywhere, and in this case, you don't have any interference with the sulfur signal from the electrolyte, but it's just from the cathode. Okay, so I'm close to the end, so I just want to show the very last work. I'm still in the same range. So previously, what I have shown was a more, let's say, was useful for spectroscopy point of view, was a more empirical approach. But of course, let's say the ultimate way or the best way is you need some theory, of course. You would like to interpret your spectra by doing some calculations. And for that, I show here the measured spectra. With the black one, it's a pure sulfur. And this is a starting point, because this is basically the only sample which you can really trust that it is clean. I mean, because with the polysulfides, you never know what is actually really inside. So we start with just a regular sulfur, and you can see on the right, this is a calculation. So this is a DFT calculation for isolated molecule with 2 different codes. So this is the work done by Marco. And also Avareich, our new PhD student, is now entering here. And you can see we can reproduce this spectra, I would say, very well. I mean, it's as good as you would. I don't think we need anything much better. So with this, I mean, this was like a first step. We are pretty confident that these calculations are okay. And after that, so we can move to the full series of these polysulfides. And then it gets interesting, of course. Then you have a DFT calculations on the left, of course, and then you have, like I have explained before, different, let's say, regarding electronic structure, there are different type of sulfur atoms within the chain. You can calculate for each. And you can have specified 3 groups of, you can see, we call it internal, terminal, and then there are even central, one in the very middle, which reflects similar like in the pure sulfur. And then when you have this, you can model your spectra as a linear combination of these two, because you know that these polysulfides, of course, they are not clean as we have seen before doing experimental synchrotron, but you can see we can fit very well the series. So that means each of these spectra measured is a linear combination of these 3 types of calculated shapes, which is good. And if you do the fit, of course, you can also extract the numbers. And this I found also very nice. So you can see this reminds roughly what I have shown before with the work at the synchrotron. So you get, okay, this is not now a theoretical, but it's just a nominal value. I mean, you know, if you take Li2S6, I mean, what is the expected number of, let's say, terminal and non-terminal atoms? And you see we get a good agreement with for the long chain polysulfides, and then we start to, of course, move away from this expected curve, and this is basically exactly the same as we have seen before. So that means the numbers that we extracted are in fact significant, so they are real, so we can also quantify this, and this I think is it's not just, I mean, to explain the spectra, but we can in fact, I mean, it's how to say, we were a bit curious whether, because the changes are not large, but it looks like it's good enough. I mean, they are representative so that such work can be done. So I will finish with the last one. So, and then the next step we have done, of course, we try to use this also we take first 3 cathodes from the previous study. And we try to, I mean, the spectra, and we try to somehow quantify. So not just to determine the charge, we want to do something, let's say, similar, because in absorption you do linear combination fitting and you somehow determine the amount of each fraction. And here we try to do the same, of course, but it's a bit more complicated because now there is electrolyte also inside. So you can see the calculations have been extended now to put into account also the electrolyte. So one needs to do molecular dynamic calculations, which changes slightly the shape of the spectrum compared to isolated molecule. And with this one, now you can try to fit this series, because here we were interested mainly in polysulfides, and you get, okay, let's say, not perfect fits, but I mean, you fit, I mean, as it is. And most importantly, again, you get even the numbers. Of course, in the fit, you will get the numbers, and these numbers, I mean, they make sense. So you can really see, I mean, the amount of the sulfur that has been converted. They're okay inside even this amount of different atoms. This is a little bit too much, and it's not exactly what one would expect. But at the moment, we focus on this first line, and this gives, in fact, a good merit of the process that has been performed in the battery. And I see absolutely no reason why one would not be able to measure this in operando, and we will do that for sure. We just need to find good conditions, because there is a problem with the probe. Protons are not really favorable, but the methodology that is here, I think it proves that the batteries could be characterized also within a lab. We were not sure about that, but now we are pretty convinced, and I think we will do this in the future in different systems. And with this, I would like to finish here. So, and just this is okay. It has not been published yet. I hope it can be published soon, but for more details, yeah, you can look here. So this was the last example from this laboratory work I have shown. So I would just like to finish here. I'd just like to, of course, acknowledgement the contributors. So from our lab, so colleagues, different colleagues, which we go to synchrotrons together, also people around the accelerator, of course. Then all the synchrotron data I have shown have been collected at the ID26 beam. So I would like to acknowledge this was a perfect, really a very, very useful for us. We have learned a lot. So the collaboration with Peter Glatzel and many people we have met there at the ID26, they are now at different positions, some of them so already. So I have not given names. And then, of course, the stuff related to the battery. This is of crucial importance. Of course, this is a collaboration with the group of Robert Domingo from National Institute of Chemistry. So they can, in fact, give you the problem. They prepare the samples, and this is a crucial part of such a collaboration, which I believe it's of mutual interest. So I'm very happy also with this one. So, and I would like to thank them all, and of course also you for your attention. I hope I have not taken too much of the time, and we can go with questions now. Thanks.
All right, very good. Thank you. Let's start with Georgi Venko had a technical question.
Hi, Matjaz, nice talk. I just wanted to ask about the crystal that you are using, because you said you are using Johansson. For example, Jerry's group is using Johann crystal for tender XES. So how important it is to use that? How big is the Johann error? Is it really necessary?
I know that Jerry is using. So now the trend is to go, of course, to the small radius, because this really boosts the efficiency and everything gets much smaller. So I like this. And generally, when you work with a large enough break angle, I think it should not be a big difference. And especially when you work this, when you move inside, basically, as we do. And Jerry is calling this, I think, dispersive. He will correct me. Then it's because you don't basically use the full crystal at once in the dispersive. So I would say it might not be that critical. So I believe, one could maybe use also the Johansson, but for sure, Johansson is a better choice because it gives you more flexibility. But I have seen the spectra we from Jerry, we have compared sometimes, and I see no problem. So the resolution is okay, and they use similar crystals, so similar angles.
I think if you have a small source, like you're at the synchrotron and focus, then Johann and Johansson are going to be pretty similar. But if you're in the lab with a large source, then we have to mask the Johann quite a bit when we get away from backscatter. And we've been working with an optics company to see if they can make a small radius Johansson, which is of course very challenging.
Yeah, but I still, I like, I would also personally like to go to smaller radius, because this, it's a bit, one needs to try. How large is this effect? Like you say, you can always mask, a bit, but generally we also work with, sometimes with very large source, and it doesn't make a huge, we have worked at for example, at Electra, so it's a bending magnet beamline on a gas. We have taken really a full, this was so wide, the beam, and there was not a major problem. But of course, we use for that purpose Johansson.
Okay, Konstantin, I see you have your hand up. You have a question?
Yeah, thank you. Yeah, thank you for the nice talk. Very interesting. My question is about double excitation, what you exemplified first on argon, but then you try to avoid it. Can it be used instead? information source? Because I guess it's also chemistry dependent.
Yeah, I mean, yes, you're right. So basically, a good question, actually. I like it. So we have, I didn't show here, but basically in all of the spectra that we have collected, for example, on sulfur standard at home with MEV, we have inside, but just for the purpose, because people are used to compare with synchrotron data, I take it out because the shift is quite large, so they are well separated from the main line. But basically, yes, it is very much sensitive. If I will show you, I mean, to the different to the chemical state of your target. So there is a large sensitivity, but what I don't like so much is that it's very difficult to calculate anything. So it's more, you see the sensitivity, okay, it is there, but one would like to have a clean case that where you can also interpret it properly. It's not just about seeing some, I don't like this approach. You see some sensitivity, you see some change, but you should be able, I think, to really, like we have done, for example, for the batteries, you need to put some theory behind. And for multiple excitation, if you have doubly excited states, I would imagine this would be very difficult. So therefore, we avoid it. But the sensitivity is there. You are right. Sometimes it can be even larger. Yeah.
So it's not used not because it is too weak, for example, just because it's unexplored.
No, it's not too weak. I mean, and even at home I can make it very strong. I mean, if I can use some heavier ion even, for example, and then it gets almost the dominant feature of the spectrum.
Even so.
Yeah.
Okay. Thank you.
All right, Yulia Pushkar, you have a question?
Yeah, your mushrooms were kind of cute spectra. So I have a biological question. So did you try to measure purified protein, and what kind of concentration of protein you need to have a signal on your lab-based system?
Yeah, I don't know. I mean, it's difficult to say. We were asked at the SRF sometimes. I mean, of course, a lot of people were interested in proteins, so there were questions to put a cryostat inside also. And but generally, I cannot answer this. I don't know what would be the lowest concentration that we could measure. We have done, but not on proteins, on some samples. Now I don't recall. It has been a long time ago. But I think with at the synchrotron, let's say on the level of 100 or maybe few hundred, but on the level of 100 ppm, yes, we could do K alpha at least, so the core to core, and to determine also the oxidation state or the something similar as we have seen in mushrooms. So on some mineral samples, I think there was like, let's say, order of magnitude, the concentrations of sulfur was ppm, and it was possible to do such speciation.
Mm-hmm.
This is my best answer I can give. But
Okay,
it's a question of, sorry.
I was just going to say, last question is from Richard then.
Hello, I was just wondering if instead of doing static measurements, if there are questions which need time-resolved measurements for these systems.
Yeah, we have never done time. I mean, of course, battery generally, this is a dynamic system, but of course, luckily it goes very slow. So otherwise, it's always interesting, yeah, if you can do time resolve, but it's always a question, yeah, how fast you should go. You know, it's a matter of the efficiency. So in your case, you have this huge the full cylinder spectrometer in Berlin. So for sure, I mean, the efficiency should be higher there, and maybe one could do, let's say, such studies. In our case, we have never done any time resolve, but generally, I don't know. I don't see any obstacle. I mean, it could be done. I don't see a big difference then, basically. Sorry,
I was more wondering in the shorter time range, so let's say pico or nanosecond range. So
yeah, but we don't have such a source, and but generally, I mean, I'm not so familiar with time resolve studies, but I have seen some work in the hard X-ray range. For example, Georgi maybe can add something. He has been experienced there, and I don't see, I mean, a big difference. So I think in a similar way, one could do also in this range. Yeah.
I think the biggest dilemma is having a camera that's fast enough based on the repetition rate of your X-ray source.
Yeah, but even I think with a slower one, you can yeah, of course, it's not like at the free electron laser. There you need, of course, to have a synchronized with the rep rate of the laser. But here, I mean, basically, as I have seen, you work with the laser on, laser off. So basically, the measurement itself, it's not so dynamic, at least what I have seen. Okay, you just need a probe, and then you just change the unit, of course, to synchronize with the bungees and so on. So I have just observed once, I remember that, so it's not straightforward, but the measurements itself are, I would say, somehow similar when you have everything set, of course.